Hello everyone, back again for another lecture of Electronics 1. Today we're going to look at amplifier models and talk a little bit about what an amplifier is, terminology you've probably heard but may not have thought about in the context of an electrical system. Okay, so what is an amplifier? So an amplifier is a device that increases the amplitude of a signal. And when you say it like that, it seems like a pretty obvious definition. Okay, usually it's increasing the amplitude of a small signal, referring back to some of the terminology that we used last day and that we're going to continue to use. Again, the signal that we're amplifying is usually the small signal component of the signal that might be in the system. Okay, the amount of amplification that gets applied, or the amount of the increase, is called the gain of the amplifier. So let's look at a simple example. Let's treat our amplifier, at least initially, as just a black box that has an input and has an output. Okay, and if we apply a signal at the input, let's call that input signal VI. Right, and let's just assume for now maybe it's a sinusoidal signal. Okay, so this is our input. Often we'll abbreviate this I/P. Okay, and that input signal, let's just for this example assume that it has a peak-to-peak voltage of 10 millivolts. And again, that's, let me slide this over here and call this 10 millivolts PP, which means peak-to-peak, from one peak of the sine wave or the waveform to the other. Okay, and if we have a look at the voltage that appears at the output after going through this amplifier. Okay, so this signal is being applied here. We're getting this signal out. We'll call this signal V out. And maybe this signal that comes out, and excuse me for not being to scale here, but let's pretend at least that this signal coming out here has a peak-to-peak amplitude of 100 millivolts. Okay, and this, as I said, is the output, which we will sometimes abbreviate as O/P. Okay, so for this particular amplifier, we can now, and as is often the case, we will define the gain of the amplifier, and the gain being a measure of the output relative to the input. Okay, so we can calculate the gain if we know the magnitude of the output and the magnitude of the input. So in this case, our output is 10 times higher than the input, because our output was 100 millivolts peak to peak, our input was 10. So in this particular example, we have a gain of 10. Okay, I just want to highlight that, right, where this, let's back up here for a second. Let's show the way this is calculated. This was calculated as 100 millivolts peak to peak over 10 millivolts peak to peak, right? And this gives us a gain of 10. And we often talk about gain when we're talking about gain and voltages. We usually give this units of volts per volt. Okay, so because, okay, so just to note here, both the input and output were voltages. Therefore, gain has units of volts per volt, right, as we labeled here. And really, volts per volt is really dimensionless. But we often still list the dimensions as volts per volt, just to make it obvious that we're talking about the gain on a voltage signal, right? Where the input's a voltage and the output's a voltage. It just adds clarity. Okay, so that's just a generic black box look at a amplifier, and in this particular case a voltage amplifier. From that we can develop a model of a voltage amplifier. Okay, so let's look at what a basic voltage amplifier model might look like. And we're going to start out with a model that's ideal. Okay, to develop this model, we require an element that's called a voltage controlled voltage source. So this is a source whose voltage is controlled by a voltage. Okay, so if I let me just show you what this looks like, and this is going to make up the main component of our ideal voltage amplifier model. Okay, so if I have a device that accepts a voltage at the input, and as a result of that voltage, produces a voltage at the output that has some gain term associated with it. Okay, I'll just put an A down here. I'll label this as a positive with a positive and negative, and here is where we would apply the input voltage, and out here I produce an output voltage, and that output voltage is a function of the gain times the input voltage. So this is my output voltage that's produced. Okay, so this, if I were to wrap this in a box here, kind of like my black box that I started with, this is my voltage controlled voltage source. Okay, so often abbreviated voltage controlled voltage source, or VCVS. Okay, so this is my voltage controlled voltage source. Okay, so the amplifier model's not really meaningful unless we connect things to it and make use of it. So let's think of it in the bigger context of how it is going to be used. So typically an amplifier is going to have some signal applied. So let's apply a signal at the input. I'm just going to show a sinusoidal source. I'll call this Vs. Okay, so this is my source. And typically we're going to have some load attached to the output of the amplifier, which it is going to drive. Amplifiers, kind of in the context of maybe you're most familiar with, might be an audio amplifier. So maybe this load is a speaker. Okay, so this is what's termed the load on the amplifier. Okay, and it's across that load that this voltage is developed. Right, so we have an output voltage that's developed across this load, and we have an input voltage here that's applied, which in this case is equal to the source voltage. Okay, a couple other bits of terminology that we are going to address when talking about amplifiers is what the input resistance is looking into the input of the amplifier, and what, let me just make sure that it's clear that this isn't part of the circuit here, and what the output resistance is looking into the output of the amplifier. Okay, and this will become clear in a second what the relevance of this input and output resistance is. Okay, so in this particular case, like I've labeled on the diagram here, the output voltage is a function of the gain, which we've called A, times the input voltage. And in this particular case, the input voltage of the amplifier is equal to exactly the source voltage. So from that, we can talk about an overall gain, which isn't all that interesting in this particular case, but we'll see where it becomes more interesting when we look at real amplifiers. But the overall gain is the output that voltage that actually gets delivered to the load divided by the source voltage, that voltage that is actually applied from the source, or is generated by the source. Well, in our case, the output voltage is the gain times the input voltage, and our source voltage is actually precisely equal to the input voltage. So the overall gain in this case of an ideal amplifier is A. Okay, so I'm just going to say as expected here. Okay, but we've made a few assumptions that maybe weren't apparent to you yet, but will be. But what assumptions have we made as we developed this model and did this calculation of gain? Okay, so what have we assumed in coming up with this model? Okay, so we've made a few assumptions. We've assumed that our source is an ideal voltage source. What do I mean by that? Well, you should have encountered at a class at some point now that voltage sources are in fact not ideal, but when we assume they're ideal, we're saying it has no source resistance. okay, which is not the case in the real world. We've also made the assumption that the input resistance of the amplifier is infinite. Okay, so we are assuming that our I is infinite. Where do we see that? Well, look, when we look in here, that connection just goes to an open circuit where the resistance would be infinity. Okay, so there's no current flowing into the input as a result of that. And we've also made an assumption that the output resistance of the amplifier is 0. Okay, so we've assumed that RO is 0. Okay, again, going up here and looking in, if I look at the voltage looking back from the output, if you think about when you're doing a Thevenin equivalent circuit and you're calculating the resistance looking back from some point, like we are here, well, this is a voltage source, and a voltage source gets short-circuited when we're doing calculating those equivalent resistances. So looking back from the perspective of that where that output RO is labeled, while we see 0 output resistance from this amplifier. Okay, so those are the assumptions we've made. But if we look at real devices, and let me pull up a couple of examples here. So just grabbing an oscilloscope, an image of oscilloscope. I just grabbed one off of Amazon here. Maybe not where you're going to buy your oscilloscope, although these are pretty reasonably priced. If we zoom in here on this segment down in the bottom where we would apply an input, because so an oscilloscope is, it's going to act like an amplifier. It has input, so it can measure small signals. I'm not sure how well you can see this. If we zoom in on that region by the inputs, you might note that it lists a resistance on the input. Okay, so right here we see a resistance that certainly isn't infinite. It is high, but we see a case of an input resistance here that's 1 mega ohm for this oscilloscope, which again is essentially an amplifier. So what about an output? So we don't have an oscilloscope doesn't really act like provide an output signal. So let's look at a device like a signal generator. Okay, so looking at another device that using these devices, because you should be a little bit familiar with them from the lab, or you will see them in the lab at some point, because most other electronic devices, although they have input and output resistances, don't show them. So here's a signal generator again that I've just grabbed off Amazon, and we look here, and maybe not quite so obvious, but it's giving the settings for this output channel, and you'll see that down here it's shown that and actually you can change the output resistance. We won't get into the reasons why right here, but this device actually has it set for an output resistance of 50 ohms. Okay, so all that to say that real amplifiers don't have input resistances that are infinite, and they don't have output resistances that are 0. They might be close, they might be very high, mega ohms, They might be low, in this case 50 ohms, but they're never quite match that ideal case. Okay, and efforts to keep these videos short, let's end this lecture number 2 here, and we'll follow up with lecture number 3 that further develops our amplifier model to show the non-ideal nature of a typical amplifier, modeling the input resistance, modeling some output resistance, and looking what impact that has on our signal and our overall gain as we looked at for our ideal amplifier.